Hello everyone, this is Arindam Biswas and I'm a graduate student from the Electrical Engineering Department. This is my final project presentation for the Bioelectricity course. In this presentation, I will be explaining the magnetoperception in birds. Now let us ask, what is magnetoperception? Magnetoperception is the ability of large variety of animals and birds to sense the geomagnetic field and utilize it as a source of directional information with the help of low frequency light wave. Different animals use magnetoperception to find proper nesting ground and food sources. For example, birds, fleas, bats, mice, pigeons, tortoise, and many more. In the paper, Magnetic Compass Orientation in Birds and its Physiological Basis, Wolfgang et al. Postulated that magnetoperception is a light-dependent primary process. It's a multi-receptor mechanism. The compass direction is collective and integrated result of extracellular recording from the nucleus of basal optic rule, the tectum octagon response according to changes in magnetic north, and the peak caused by distinct spatial directions. This postulation is supported by some behavioral experiment. In those experiments, different spectrum of light was exposed to the bird's environment, and according to the light induced, there are some examples. Now, how does this work? So, according to Thorson Reeds et al., in the paper, a model for photophosphor-based magnetoperception in bird, they explain the photoreceptor that's liable for initiating the magnetoperception. It's called cryptochrome. Now, cryptochromes are a class of flavoproteins that are sensitive to blue light. They are found in plants and animals. Cryptochromes are involved in circadian rhythms of plants and animals. They are also responsible for sensing of magnetic fields in number of species. Contradictory statement is that while magnetoperception is related to the magnetic field of the Earth, but the cryptochromes is light dependence. And this light dependency in the form of magnetoperception is proved according to different behavioral experiments. From the paper, magnetic compass of birds is based on molecule with optimal directional sensitivity by Thorson Rich et al. It was explained a light-induced electron transfer reaction creates a spin-correlated radical pair with singlet and triplet state. External magnetic field of the intensity of the geomagnetic field can interfere with the dynamics of the triplet singlet interconversion and thereby modify the yields of reaction products. The magnitude of the response depends on the orientation of the radical pair with respect to the direction of the external magnetic field. By comparing the responses of receptor cells with different orientation as they are found in the eye, birds could thus obtain information on the direction of the external field. They also proposed that a radical pair-based magnetic compass in birds may comprise an ordered system of electron donor or acceptor pigments, absorbing in the required wavelength range in close proximity to electron acceptor or donor reaction. What does that mean is this reaction which causes the magnetoperception is sensitive to a specific wavelength of light. The experimental proof of specific wavelength dependency was shown in the paper by Ulsko et al. Here, They showed when the European robins was put under blue, turquoise, and green light, their orientation was natural and it was preserved. But when they are exposed to yellow and red light, they disoriented from their natural course. That proves that the magnetoperception is indeed a very specific wavelength dependent of light. So far, we have discussed the first stage of radical pair generation. Now let us look how geomagnetic field affects the magnitude of radical pair, which in turn gives the bird's sensitivity of orientation. Two interesting facts was found by Wilsko et al. First, the geomagnetic perception is based on an inclination compass, not polarity, and it's restricted to narrow intensity range. An inclination compass means that directional information is derived from the inclination of the field line rather than from their polarity. So more inclination means the amplitude of the triplet and singlet pair will be changed and thus more inclination. Now, in northern latitudes, the field lines of geomagnetic field run from south up towards north down. Reversing the horizontal components results in the field lines running from north up towards south down, a situation that causes the birds to reverse their headings. When the vertical component of the magnetic field is inverted, the field lines run from south down towards north up. Their axial course, however, is identical to that which results from a reversal of horizontal component, and as in that situation, birds reverse their directional preference. When both components are reversed, axis of the field lines remains constant, just changing its polarity. Birds respond in the same way as they do in the geomagnetic field. As a consequence of this functional mode, which was found in all the species tested so far, the aviation magnetic compass does not distinguish between magnetic north and south, but between poleward, the direction where the axis of the field lines forms the acute angle with gravity, and equatorward, where this angle is larger than 90 degrees. At the magnetic equator, where the field lines run horizontally, the two angles are equal and the inclination compass provides bimodal information. Now we can summarize the magnetoperception process by three steps. First, initiation, in which the radical pair generates; inclination, which according to the inclination of geomagnetic field, the amplitude of the pair is determined; and according to the horizontal and vertical component of electromagnetic fields, the direction is determined.